Hello friends, welcome to the lecture number 6 of convective heat transfer. In today's class, we'll be looking at another method of solving convective heat transfer problems, which again involves a certain level of approximation and simplifications. Classically, the partial differential equations were insurmountable at some point in time. They could not be solved. And so there were several methods that were evolved. So we talked about the order of magnitude approach, which is a very intuitive and insightful method, which basically gives you the form of the various solutions, but without the detailed solution, and therefore the necessary constants were missing. But at least it gives you an insight into what kind of behavior with respect to the various non-dimensional numbers the solution does exhibit. Then we went into the similarity solution method, where a certain class of problems in which the solutions become self-similar in one direction. Let us say the boundary layer problem, for example, at different locations of x, the solution is only getting stretched by the thickness of the boundary layer, as this thickness of the boundary layer grows as a function of x. So if I call the thickness of the boundary layer as delta, which is a function of x, then y by delta is a scaling variable with respect to which the entire boundary layer profile can be scaled. So then if I normalize the u by u infinity, that is the velocity, local velocity divided by the free stream velocity, and plot it against y by delta, then at all cross sections, at all the values of x, I get the same non-dimensional profile. So now this is called similarity, and using this or exploiting this, we arrived at methods of simplifying our partial differential equation into an ordinary differential equation, which could be then solved using methods that are useful in solving ordinary differential equations. These ordinary differential equations are also nonlinear, and therefore they cannot be analytically solved, but then they are solved using numerical methods or asymptotics, and using that you are able to get the solutions, which basically give you the skin friction at the wall and heat transfer coefficient at the wall, which are the results that we are seeking in convective heat transfer. In today's class, we will be looking at a third approach, which is called the integral approach. Basically, what is being said is that since the boundary layer is a very thin entity in which the entire phenomenon of heat transfer and friction are determined, the integral approach basically says, okay, why do we want a complete profile of velocity or temperature in the boundary or in the boundary layer? Why can't we just work with the gradients at the wall and the boundary layer thickness, so that from that itself we'll be able to get the solutions? So what we normally do is not worry about exact solutions of how u varies with y or how temperature varies with y, but make approximate profiles, let's say straight line or quadratic or cubic kind of profiles, and integrate that profile over the boundary layer in order to predict the skin friction or heat transfer coefficient or Nusselt number with a certain degree of approximation. Okay. So today's class will basically focus on this method. In order to do this, basically what we normally do is to integrate the boundary layer equations across the thickness of the boundary layer. Okay. So when I say boundary layer, you have two different boundary layers that we normally deal with. One is a velocity boundary layer, the other is a thermal boundary layer. Velocity boundary layer is the thickness of the region within which the velocity goes from 0 to free stream velocity, and the thermal boundary layer is the thickness within which the temperature goes from the wall temperature to the free stream temperature. So what we will do today is to take the simplest problem of a flat plate boundary layer and look at how, for given constant wall temperature and constant free stream velocity and free stream temperature. Since in flat plate boundary layer the free stream pressure is constant and independent of the x and y, so we deal with a much simpler problem. The problem can be solved even when these terms do exist and they exhibit certain ruling, depending on the configuration. For example, if I have a shape of a body over which the flow is going, then the shape of the body determines the velocity profile or the pressure profile of the free stream. It can be generalized for that, but we will start with the simplest problem in order to understand the approach. Okay, so that is basically what would be the agenda of today's lecture. Okay, so let's move to the whiteboard and start the discussion there. Okay, so we'll talk about integral method for laminar boundary layer over a flat plate. So what are the equations that we'll be dealing with here? The laminar boundary layer over a flat plate basically involves the continuity equation, which is del u by del x plus del v by del y equals 0. So let's call this as equation number 1. Then u del u by del x plus v del u by del y equals mu del squared u by del y square. So we have neglected the del square u by del x square by the boundary layer approximation, and we have assumed constant properties. So the density from the left hand side has gone to the right hand side, okay, and become mu by rho, which is mu. This is, let's say, equation number 2, and the energy equation u del t by del x plus v del t by del y is alpha del square t by del y square. This is equation number 3. So in integral method, it's always normally preferred to recast these equations in what we call as the conservation law form. And an equation is said to be in the conservation law form when the coefficients that are there are not dependent variables, so they are absorbed inside. So how do you do that? In order to do that, you add to equation number 2 the equation number 1 multiplied by u. So what happens? You get a u del u by del x plus u del v by del y added to this one. So u del u by del x plus u del u by del x is 2u del u by del x, which is del by del x of u square by 2. Okay, so del by del x of u square, and here you get a u del v by del y plus v del u by del y, which will basically be del by del y of uv. Okay, so that's basically what you do. Similarly, for this equation, you multiply this continuity equation by t and add to this, so you will get a del by del x of ut plus del by del y of vt here. Okay, and the right hand side remains exactly what it is. Okay, so that is normally called the conservation law form. So there will be no coefficient of these partial derivatives, which are functions of x and y, okay, or which are basically functions of the dependent variable. So if I do that, so basically I write second equation plus u times the first equation gives me del by del x of u square plus del by del y of uv is equal to mu del square u by del y square, and similarly 3 plus t times 1 gives me del by del x of ut plus del by del y Vt is equal to alpha del square t by del y square. So I call this as 2a and 3a. Okay. So now in the next slide, we'll start with the momentum equation. So the momentum equation 2a is del by del x of u square plus del by del y of uv is equal to nu del square u by del y square. So if I integrate both the left hand side and right hand side across the thickness of the boundary layer, so then I get an integral from 0 to delta of this whole thing dy is equal to integral from 0 to delta this thing into dy. Okay, so this is basically what we try to do. Then what will happen? I get and let me separate out these terms. So I'll get an integral from y is equal to 0 to delta of del u square by del x into dy, plus this can be integrated out because there is a del by del y, so you will get a uv at delta minus uv at 0. Okay, so that is the definite integral. This becomes equal to, this can also be integrated, nu will be outside, del u by del y at delta minus del u by del y at 0. Okay, now let us look at the terms that we have presently got. So this uv at 0, both u and v are 0 at the flat plate because y is in this direction and x is in this direction. This y is equal to 0 is on the plate. So on the plate both u and v are 0. So this is no slip and impervious plate. So no slip meaning there is no sliding motion along the wall, so u is 0, and impervious means there is nothing coming through the wall and therefore v is 0. That is why both u and v being 0, this term becomes 0. Similarly, in the boundary layer, the u at y is equal to delta becomes equal to u infinity, and the gradients in u disappear at delta, and therefore this is 0 because edge of boundary layer, all gradients vanish. Okay, so now this is what remains. There is a term called u at delta, and u at delta is actually u infinity, and v at delta we can determine from the continuity equation. So let's do the continuity equation. So integrating from 0 to delta of del u by del x plus del v by del y dy equal to 0. This is from 1. Okay. Now if I integrate this, what do I get? I get integral from y is equal to 0 to delta of del u by del x dy, plus this can be integrated out, so it will be v at delta minus v at 0 equal to 0. Now v at 0 is 0 because of impervious condition. There is nothing flowing through the wall, so this is 0. So this tells me that v at delta is equal to negative of del u by del y del x dy. Okay, so this is the next equation that we will use. So let's call this as let's say equation. So we had equation 3a here. So let's call this again. This is actually 2b because this is the momentum equation in a different form, and this is, let's call it as 1b. Okay, which is because continuity equation integrated in this form. So now we can substitute for V delta in this equation from here and combine, and we have to do something to get this different derivative out of this. So for that we use what is called the Leibniz formula. Okay, so what is the Leibniz formula? It says integral of d by dx of integral of f of x y dy from y is equal to a of x to b of x. This can be written as equal to integral from a to b of del f by del x dy plus db by dx minus dA by dx. Okay, so this is the way we write it. So in this particular case, if I use this expression, this dB by dx and dA by dx would go off, and this basically would simplify to this term is equal to this in most of these cases. So integral from 0 to delta of del u squared by del x into dy would actually become d by dx of integral from 0 to delta of u squared dy. Okay, and similarly from the other equation, del by del x or del u by del x from 0 to delta dy would actually become integral of u dy from 0 to delta d by dx of that. Okay, so if I use these two into equation 2b, so substituting in 2b from this and 1b. And we call this, let us say, as 4. Then we get d by dx of integral from 0 to delta of u squared dy minus u infinity into d by dx integral from 0 to delta of u dy is equal to nu times, with a negative sign, del u by del y at 0, right? So in this equation, basically this term becomes d by dx of u squared dy, and this becomes u at delta is u infinity, and v at delta is negative of integral of del u by del x dy, which becomes d by dx of u dy. Okay, and the right hand side term, there is a minus del u by del y at 0 multiplied by nu. So that is the term that remains. So this is your equation. So we call, let's say, as 2c. Okay. Now this equation, let's combine the two terms inside the d by dx. So this u infinity is a constant, so I can take this in. So it becomes u infinity u, and u square minus u infinity u. So it becomes d by dx of integral from 0 to delta of u times u minus u infinity into dy. Okay, because this is u times u and this is u times u infinity with a minus sign. Okay, this is equal to minus nu del u by del y at 0. So this is term corresponding to the shear stress. This minus sign I can absorb on this side. So what I'll get is, I'll take out the minus sign from here, and I'll also rewrite this as u infinity minus u. Okay, so it becomes u infinity minus u dy. This is logical because your u infinity is greater than u all the time. So this is your equation. So let me call this as equation A, which is the first integral equation. This is the momentum integral equation of the boundary layer. Okay, so this is the first equation that I'll be solving. We'll come to the energy integral equation later. Let's try to solve this by assuming a certain velocity profile so that the only unknown in this equation will be delta, which I can determine. Okay, so that is the objective of the integral method, to obtain the expression for delta and then using that for writing the value of the shear stress. Okay, so here we go. So let us assume, so we can assume any shape of profile. We can assume a straight line, we can assume a quadratic, we can assume a cubic. The most classic examples that are given in textbooks is a cubic, so I'll do that here. Let's assume a cubic velocity profile. In the boundary layer. So let us use a non-dimensional form. So let us say u by u infinity is equal to a plus b into eta plus c into eta square plus d into eta cube, where eta is y by delta. Okay, so this is the same notation that we use in the similarity solution module also, that we said y by delta is eta. So if I use that, and what are the conditions for this velocity? At y equal to 0, that is eta equal to 0, you have u is equal to 0, okay, or u by u infinity is 0. So we can call this as, let's say, u tilde. Okay, so u tilde is 0 at y is equal to 0, and at y is equal to delta, that is eta equal to 1, u tilde is 1 because u becomes equal to u infinity. So these are the two conditions that I have. In addition to that, because there is a cubic equation, we need 4 conditions. So the second condition would be that at y equal to delta, that is eta equal to 1, the gradient of u vanishes. So I can say del u by del eta equal to 0. So that is gradient vanishes at the top of the boundary layer. The fourth condition can be arrived at from the basic governing equation itself. So if I go to equation number 2, that is here, and look at what happens at y is equal to 0. At y is equal to 0, if I apply this equation, u is 0 and v is 0, so these two become 0. So then you get, because nu is not 0, you get del square u by del y square equal to 0 at y equal to 0. Okay, so we'll use that condition. So from 2, at y equal to 0 or eta equal to 0, I would get del squared u by del y square, and this you can write in terms of u infinity and this one, so the delta, and since they are not 0, you can just write equal to 0, which is also equal to del squared u tilde by del eta square. Okay, so these are the 4 conditions that I have. So using those 4 conditions, so if I apply the first one at y is equal to 0, so these become 0, so a is equal to 0. So from this condition, from the first condition, a is equal to 0. Okay, now if I use the second condition, that is here, then from 2, since a is already 0, I can write only the other 3. So at eta equal to 1, so it becomes b plus c plus d. So you get b plus c plus d equal to 1. If I use the third condition, from 3, So if I take the derivative of this, this will go off. So it will be b plus 2c eta plus 3d eta square, and at eta equal to 1, it will become 1, 1. So this will become 2c and 3d. So I get b plus 2c plus 3d, and this becomes equal to, this is 0. So this is 0. So from these two, I can eliminate b by subtracting. So I get this minus this. So if I subtract the second equation from the third equation, I get c plus 2d equal to minus 1. Correct? Now from the fourth equation, which is the second derivative with respect to eta, so this will go off and this will go off. So you will have, initially you had a 2c eta plus 3d eta square. Now that would become 2c plus 6d eta. So, and at eta equal to 0, the d will disappear. So there will be 2c, and that will be equal to 0, gives c is equal to 0. Okay, so substitute that in this equation. So then you get 0 plus 2d is equal to minus 1, gives d is equal to minus half. And if I substitute both of these into this equation, so I get c is 0, b minus half is 1, so b is equal to 1 and 1 plus half, which is 3 by 2. So then I can substitute all of these into this equation. Then I get u tilde is equal to a is 0, b is 3 by 2, and c is 0, and d is minus half. So 3 by 2 eta minus half eta cube. Okay, so this is your expression. Now if I substitute this profile into the equation that we had just derived, the equation A, so I write this in terms of u tilde and eta and substitute from that equation. So what do I get? So if I write A gives integral d by dx and integral from, let's say, 0 to y by delta, so it becomes eta is equal to 0 to 1 of, in this equation, if I want to write in terms of u tilde and eta, this since u by u infinity is u tilde, so I can write u is equal to u tilde into u infinity. So if I do that, and I take one u infinity out from here and one u infinity out from the bracket, so I get a u infinity square, I'll get a u tilde multiplied by 1 minus u tilde. Okay, so that's what I'll get. And this, since y by delta is eta, so dy by delta is d eta. Okay, so dy will be equal to delta d eta. So I can take out the delta because the integral is with respect to y, and delta is not a function of y. So I'll get a u squared delta out of the integral. I'll get u tilde into 1 minus u tilde d eta. Right. So that's basically what I'm going to write now. Let me make space for that. So there will be a u infinity squared into delta, and then there is an integral from 0 to 1 of u tilde into 1 minus u tilde theta. Correct? This is your left hand side, and that is equal to mu times, on the right hand side you have a del u by del y at 0. So del u by del y will actually become u infinity by delta multiplied by del u tilde by del eta at 0, because y is equal to 0 and eta equal to 0 are the same, so they can do this. So on the right hand side you have del u by del eta at 0, and since u is this, if I take a derivative of this, it will become 3 by 2 minus 3 by 2 eta square, and at 0 this will go off, so there will be a 3 by 2. So del u by del eta at 0 del u by del eta is nothing but 3 by 2 minus 3 by 2 eta square, and at 0 this becomes 0, so it will become 3 by 2. So I'll be able to write this as 3 by 2 into u infinity nu by delta. Okay, so that is the right hand side. Now let us come to the left hand side and try to simplify this. What happens to this integral? Integral from 0 to 1, if I substitute for u infinity, for u tilde as 3 by 2 eta minus half eta cube into 1 minus 3 by 2 eta plus half eta cube d eta, right? So I substitute for u in terms of this profile and simplify this. So this becomes integral from 0 to 1 of, let's write down all the terms one by one. So 1 multiplied by these two will come first. So it will be 3 by 2 eta minus half eta cube. Then I'll get a minus 3 by 2 eta multiplied by each of these. So that will become plus 9 by 4 times eta square. And okay, so this is a plus and this is a minus, so it will be a minus. So this is a minus. So then there will be a minus of minus plus 3 by 2 into half will be 3 by 4. So plus 3 by 4. And there is a eta and a eta cube. So eta to the power of 4. And then we have half eta cube multiplying this. So it's a plus 3 by 4 into eta cube is eta to the power of 4. Okay, and then there is a minus 1 by 4, and this is eta cube into eta cube, eta to the power of 6 eta. Right, so that is the integral that I will get by writing this. Okay, so now if I try to simplify this expression, first integrate this. So this becomes eta squared by 2 between 0 and 1. So it is 1 by 2. So this integral becomes equal to, so there will be 3 by 2 multiplied by half, which will be 3 by 4, minus the half multiplied by eta cube becomes eta to the power of 4 by 4. So it becomes minus 1 by 8. Is that right? And then the next one, 9 by 4 minus 9 by 4 multiplied by, this is eta squared becomes eta cube by 3. So 1 by 3, so it will become minus 9 by 12, right? Plus 3 by 4, and this eta to the power of 4 becomes eta to the power of 5 by 5. So 1 by 5 multiplies this, so it becomes 3 by 20. And then this is 3 by 4 multiplied by eta to the power of 5 by 5. So again plus 3 by 20 and minus 1 by 4, and this is eta to the power of 7 by 7, so it becomes minus 1 by 28. Okay, this 9 by 12 and 3 by 4 get cancelled between the two, okay, each other. And if I take an LCM of this, this becomes 3 by 10, right? The sum of these two is 3 by 10 and 1 by 8. So if I take an LCM of these and simplify, so it becomes, this is 2 into 4, this is 8 is 2 into 4, and this 10 is 2 into 5, so I write only the 5 here because 2 is already there, and this is 4 into 7, the 4 is already there, so I'll just write 7. So these are the terms that are there. So this minus 1 by 8, so there is already 8 here, so there is 5 into 7, 35, so it becomes minus 35. Okay, and there is a plus 3 by 10. 10 is there, so the 3 will get multiplied by 4 into 7, 28. So it will become plus 3 into 28. Okay, and minus 1 by 28. So this is a 7 into 4, 28 is there. So there is a 10. So there is a minus 10. So what comes out here? 28 into 3 is 84, and 35 plus 10 is 45. So you get a 39, right? So this is equal to 39 divided by, what is on the denominator? 2 into 4, 8, into 5 is 40, into 7 is 280. Okay, so that is the integral. So now if I substitute that integral, okay, let me write it so that I can save some space. So this is equal to 39 by 280. Okay, so I substitute for that in this integral, so I get a d by dx of 39 by 280 into u infinity squared delta is equal to 3 by 2 u infinity nu by delta. So now I can write this, u infinity is a constant, so I can bring it out. So 1 u infinity gets cancelled between these two, and I can bring this constant on this side. So I can write delta into d delta by dx is equal to 280 divided by 39, and the u infinity goes here. Then you have into 3 by 2 nu, 3 by 2 nu, right? So now if I simplify this, this cancels for a 13, and this cancels for a 140. Okay, so this is equal to 140 by 13 multiplied by nu by u infinity. Is it correct? So now if I write this left hand side as d by dx of delta squared by 2 is this, then I can integrate this, saying that delta squared by 2 is equal to 140 by 13 into nu x by u infinity plus a constant. And in order to evaluate that constant, we say that at x is equal to 0, which is the leading edge, the thickness of the boundary layer is also 0. So the constant is 0. Okay, so this goes off. So you get delta squared by 2 is this. So that gives me the expression for delta by x. Okay. So what will happen there? If I bring the 2 to this side, it will become 280 by 13, and I write a delta by x the whole squared, and then there will be a x squared dividing here, so you get a u infinity by nu x, which is 1 over Reynolds number. Okay, so that is exactly what we are looking at. Delta by x the whole square is equal to 280 by 13 into 1 over Rex. Okay. So that's what we'll write next. So it says delta by x the whole square is actually equal to 280 by 13 into 1 over Rex. Okay, so if I take the square root of this, I get delta by x is square root of 280 by 13 into REX to the power of minus half, and if I calculate this, it gives me 4.64 REX to the power of minus half. Okay, so if I compare it with the similarity solution, which I get by integrating the whole thing using whatever method, I get delta by x is 4.92 into REX to the power of minus half for u by u infinity is equal to 0.99, because this is an asymptotically approaching value. So when I take the value at 1% from the free stream velocity, the value is 4.92. So the approximation is decent with a cubic profile. You can see the different solutions that are given in Bejan. Bejan actually tries to generalize this whole thing, and instead of the cubic profile, he takes m of eta, and that m, he says, can be linear, can be quadratic, can be cubic, can be a half sine function, and so on. And he has given the results for them tabulated. So let me just write them quickly. So from table 2.1 in Bejan, for linear profile, that is u tilde is equal to eta. Okay, so this is a straight line profile. So what you assume is at the wall it is 0, and at the delta it is 1, and after that it is u infinity. So inside the boundary layer, y by delta is the same as u by u infinity. That's a straight line. So this is the profile, and for this you get delta by x as 3.46 REX to the power of minus half. So this REX to the power of minus half comes anyway, because that is the thing that you also obtained using the order of magnitude analysis. So the boundary layer thickness always goes to square root of REX, the negative square, the negative square root of 1 by square root of REX, but the constant gets refined as your profile gets refined. So then equal to eta by 2 multiplied by 3 minus eta square, which is the same as the profile that we have got, 3 eta by 2 minus 3 by 2 eta cube, and for this it is 4.64. And if I use a half sine profile, which is equal to sine of eta pi by 2. Okay, so it's like a half sine profile that you use. So the sine profile is, full sine profile is this. So here you take it as pi by 2. So this is this profile that you get. So here it reaches a 0 gradient, and here it will have a different gradient. So using that, if I get, then I get a 4.8. Okay, so this is the thing that he compares. Now we can also look at the skin friction coefficient CF. Okay, what is skin friction coefficient CF? CF is tau wall divided by half rho u infinity square. And what is tau wall? Tau wall is mu del u by del y at 0 divided by half rho u infinity square. And if I write this in terms of the non-dimensional quantities, then you'll get mu times u infinity divided by delta into, this is 3 by 2 which is del u tilde by del eta, divided by half rho u infinity square. So if I simplify this, so this 2 gets cancelled with this 2, and I get 1 u infinity here and 1 u infinity here getting cancelled. So I'll have a rho u infinity by mu, I multiply and divide by x, then I'll get 1 over Re x multiplied by x by delta multiplied by 3 by 2. This is what I get. And for x by delta, if I substitute from these expressions, then I get the expression for so if I substitute 4.64, so this actually becomes Rex to the power of half divided by 4.64. Correct? Because delta by x is 4.64 divided by Rex to the power of half. So if I do that, then 1 Rex to the power of half gets cancelled out. So there is a Rex to the power of half in the denominator. Then you get a 4.64 into 2 by 3 in the constant. So that gives me 0.6466. Rex to the power of minus half. Okay, so if I compare this with the similarity solution, for the similarity solution this value is 0.664. Okay, so Bejan gives the values for CF also in his table. Let me quickly give you those values. Yes, so you get CF values for linear profile. It is 0.577. For cubic profile it is 0.646, and for sine profile it is 0.654. Okay, so this is the thing, and similarity you get 0.664. So that is your expression for the velocity profile. Okay, so this is the velocity boundary layer solution that we have obtained so far. Okay, we still now have to derive the solution for the thermal boundary layer. So that is the next thing that we will be doing. And in thermal boundary layer, I'll do only one of the cases. The other case I will let you study from textbooks. So we will be dealing with one case, which is Prandtl number greater than 1. That is the case that I'll be doing, where the thermal boundary layer is contained inside the momentum boundary layer. With the case where the thermal boundary layer is bigger, you need to integrate it in 2 parts, which I'll let you do as you can study it from textbooks, and maybe we can think of an assignment in doing that. Okay, so integral energy equation for a flat plate. So you start with equation B. Okay, so the equation B, you have to start with assumption of a temperature profile. Assume theta, which is T minus T wall divided by T minus T infinity divided by T wall minus T infinity. Okay, so this is equal to A plus b y tilde plus c y tilde square plus d y tilde cube. Why am I writing a different symbol here and not eta? Because this is y tilde is y divided by delta T, which is the thermal boundary layer thickness. So we are actually writing the energy equation only for the thermal boundary layer. You cannot write it for the entire boundary layer because it is valid only for the thermal boundary layer. Okay, so if I have to use eta and this concurrently, then I'll need to have a relationship between delta and delta T, which is what we will be obtaining using this whole derivation. So I will do it rather quickly. I'll not go in detail of every step, but I'll write down the steps so that you can derive it and check it for yourself. So B equation, if I write it in the non-dimensional form, it gives me d by dx of actually integral u into t minus, you actually have a, okay, so we have not derived that equation in that form as yet. So basically I have to use the Leibniz formula to get the you start with this equation and then integrate it over the boundary layer just exactly as we did for this, and simplify it. Then what we will actually get is an equation which is very similar to A. So I will skip the derivation of that in complete detail, but I'll write the final equation for saving time. Otherwise this lecture also will become much longer like the previous ones. So suppose I write this, then it actually gets me u into t minus t infinity minus t so it becomes u into t infinity minus t dy is equal to alpha del t by del y at y is equal to 0. This is the equation that it will come to. So I would let you do the derivation of this by yourself. Derive by integrating b, integrating equation. Did I already write an equation b for you? No, I didn't write an equation b for you. It's actually equation a only that I have written, but we'll need to derive the equation b in the same form, right? So you can do the same process as we did for the momentum equation. That is, take the energy equation, which is del by del x of ut and del by del y of vt. So that is the equation that you will be will be taking this del by del x of ut, del by del y of vt is equal to alpha del square t by del y square. Integrate both sides with respect to y between 0 to delta t. Okay, you are not going to integrate it from 0 to delta, but 0 to delta t. Then on this you would apply the Leibniz rule. On this it becomes vt at delta minus vt at 0. At delta, t is t infinity, and v at delta is substituted from the continuity equation exactly as we did the last time, and this becomes del t by del y at delta minus del t by del y at 0. Del t by del y at delta actually vanishes by the definition of the boundary layer, and therefore there is a del t by del y at 0 with a negative sign. So if I write this, I'll actually get t minus t infinity. So if I take this in there, it becomes actually t infinity minus t, the minus sign on the other side, and that's how you get this equation. You get a u into t infinity minus t dy is equal to this, Now if I try to normalize this in order to write the equation, so I have to write in terms of u tilde and theta. So then I'll get d by dx of the u infinity will come here, and dy would become delta t dy tilde. So this is going from y tilde going from 0 to 1, and this will be u tilde. And okay, there's some more space required before we do this. The theta would be actually t minus t infinity by t wall minus t infinity. You have a t infinity minus t, so I'll put a t wall minus t infinity here in order to be able to write in terms of theta. So then I get 0 y tilde equal to 0 to 1 of u tilde multiplied by minus theta, okay, because it's a t infinity minus t, minus theta into dy tilde. Okay, so this is your integral. This is equal to, if I write in terms of this, then you get an alpha into this del t by del y is the same as del of t minus t infinity by dy, because t infinity is a constant. So I can do that. So I'll then have a t wall minus t infinity multiplied by and divided by delta t del theta divided by del y tilde at y tilde equal to 0. Okay, so this is your right hand side. Now if I do the same fashion, the calculation of A, B, C, D for this condition, theta is equal to 1 at so the t minus t infinity is the same as t wall minus t infinity at y is equal to 0, or y tilde equal to 0, implies A becomes equal to 1. Okay, then you have theta equal to 0 at y tilde equal to 1 gives 1 plus b plus c plus d equal to 0, or b plus c plus d is minus 1. Okay, then the third condition, del theta by del y tilde equal to 0 at y tilde equal to 1 tells me b, the A term gets differentiated out to 0, so b plus 2c plus 3d, because you get 2c y tilde plus 3d y tilde square, and at 1 these two become 1, so it's 2c plus 3d, and this is equal to 0. So from these two, if I eliminate b, I should get a c plus 2d is equal to, so if I subtract this should become 1. Okay, from these two I get c plus 2d is 1. And the fourth condition, in the same fashion as before, at y is equal to 0, you get a d squared t by dy square is 0. So del squared theta by del y square equal to 0 at y tilde equal to 0 means it actually tells me c is equal to 0. Okay, so in this then you get d is equal to half, and if I substitute into this, c is 0 and d is half, so this goes here, it's 3 by 2, so b is minus 3 by 2. So then a is 1, so you get theta is equal to 1 minus 3 by 2 y tilde plus half y tilde square. Okay, so this is the expression that you would get. So you can put that into this and put u in terms of y by delta and not y by delta t. So you get a u in terms of eta and theta in terms of y tilde. Now we'll need to reconcile that. How do we reconcile that? We'll write d by dx of u infinity. Okay, then t wall minus t infinity will be there. This delta t, we don't know delta t, so okay, so we'll right now keep it as delta t, and then this u we'll write in terms of eta, but eta is y by delta, so we have to have a variable which is delta t by delta. So we'll so eta is y by delta, and we'll write it as y by delta t into delta t by delta, and this y by delta t is nothing but y tilde, and this, if I call it as a certain capital delta, then eta will be equal to capital delta into y tilde, and this capital tilde is also a function of in the same way as delta and delta t, it's also a function of Prandtl number and so on. So what will happen is there will be a t wall minus t infinity. Just hold a second. Okay, so I write this is, there is a delta t here, and integral from 0 to 1, this is y tilde going from 0 to 1, and you get this u tilde, which is nothing but 3 by 2 eta, which is delta times y tilde, minus half will be delta cube and y tilde cube, this is, and then minus theta, so that will be minus 1 plus 3 by 2 y tilde minus half y tilde cube dy tilde. Okay, so let me remove all of these things which we did as well. So this is your left hand side, and this will be equal to the right hand side, as we had shown here, is equal to alpha t wall minus t infinity by delta t into this. And what is del theta by del y at y tilde equal to 0? If I write del theta by del y tilde, which will be, this is 0, and I get a minus 3 by 2 plus half y square, so it will become y cube by 3, right? So it will become, sorry, it's differentiated, so it will become 2y, so it will become y tilde. Now at y tilde equal to 0, this becomes at 0, this becomes equal to minus 3 by 2. Okay, so we can put the minus 3 by 2 in place of this, so it will become a minus 3 by 2 alpha into t wall minus t infinity by delta t. Minus 3 by 2 alpha into t wall minus t infinity divided by delta t. Okay, so we multiply and simplify this, and then you get an expression which is in terms of capital delta, because now it's not a single variable, it has two. So if I simplify this actually, you can do that exercise, and it should come to 3 delta by 20 minus 3 delta cube divided by 280. So this is what it should come to. So if I substitute that, okay, I'm just skipping the algebra, allowing you to do that for yourself. So then there is a negative sign that was here, that was got absorbed in this one. Okay, so with a minus sign, of course. This is this. Okay, so it's actually 3 delta cube by 280 minus this. So if I substitute this, the negative sign getting cancelled with the other side, and t wall minus t infinity can get cancelled from this side to this side because we are keeping a constant t wall, and the u infinity can go to this side and delta t can come to this side, and then we will get an equation which has this form. It's delta t into d by dx of delta t multiplied by 3 delta by 20 minus 3 delta cube divided by 280, okay, is equal to the minus sign has got cancelled, so you get a 3 alpha divided by the u infinity from this side has gone here, so you get a 2 u infinity. Okay, now this is the expression that I have. Now what I'll try to do is to use the fluid mechanics result of the small delta. So since delta t by delta is capital delta, so I'll write delta t as capital delta times delta, and then bring the small delta to the right hand side and substitute for delta here. So that's basically what I will do. So what I get then is delta times I will okay, so before doing that, okay, so I'll just write the delta times d by dx of, this will also become delta into delta, so there will be a delta that is staying here, and the capital delta will go in, so you'll get a 3 delta square by 20 minus 3 delta to the power of 4 by 280 is equal to, this delta would have come here, so 3 alpha by 2 u infinity delta. Okay, now this delta we know as a result from fluid mechanics, so I don't have to worry too much about this, and this delta also I can substitute from there. So then what happens, I take one case where I can simplify it further. For the case of Prandtl number much greater than 1, in which case delta is much bigger than delta t, or capital delta is much less than 1, in which case delta to the power of 4 is much less than delta square. So this term can be deleted or neglected as compared to the first one. So then the simplification of this equation becomes this, that you get a capital delta into d by dx of delta into 3 delta squared by 20 is equal to, or is approximately equal to actually 3 alpha divided by 2 u infinity delta. Now I differentiate this because this is also a function of x and this is also a function of x, and simplify it. So this 3 by 20 I can take it to the other side. When I differentiate this, I'll get a 2. So I do that simplification, then eventually I'll get delta cube is equal to 13 divided by 14 PR. Okay, and this is nothing but delta t by delta, the whole cube. So I'll be able to relate delta t with respect to delta using this expression. So once I have got this expression, if I write the expression for heat transfer coefficient or the Nusselt number, then the h into T wall minus T infinity, which is the heat flux from the wall at any given location at x, this is equal to minus k del T by del y at the wall at y is equal to 0. And if I write it in terms of theta and y tilde, I get this is minus k into T wall minus T infinity divided by delta t multiplied by del theta divided by del y tilde at 0, and this is minus 3 by 2. So this is, I get 3 times k into t wall minus t infinity divided by 2 times. I'll be able to write this in terms of, so delta t by delta is equal to 13 by 14 whole to the power of 1 by 3 into PR to the power of minus 1 by 3. This is what we got from this expression, 13 by 14 raised to the power 1 by 3 to PR to the power minus 1 by 3. And if I substitute that here, then I'll get 13 by 14 to the power of 1 by 3 works out to 0.9756. So 0.9756 delta PR to the power of minus 1 by 3. Okay, now if I bring things here and say, okay, NUX, which is HX into X by K, so I multiply and divide by X, I multiply by X on both sides, so I get the K goes to the other side, the T wall minus T infinity gets cancelled between these two, so then I get an expression which is convenient to evaluate the result number. So I get this is equal to 3 by 2 into 1 over 0.9756 multiplied by I'll get an x by delta into PR to the power of 1 by 3, and this x by delta I can substitute from earlier result as REX to the power of half divided by 4.64. Okay, so this is your fluid mechanics result for this cubic profile. So if I substitute this, I get this is equal to 0.331 REX to the power of half and PR to the power of 1 by 3. This is NUX. And you remember that this result was like 0.332 in similarity solution. Okay. Now, what we have not done is what happens when delta is much smaller than delta t, or capital delta is much less than 1, in which case, sorry, capital delta is much greater than 1. Sorry. Then you might need to, so if it is much greater, then you can neglect the thermal boundary layer and assume that for the entire velocity boundary layer, you can neglect the thermal velocity boundary layer and assume that for the entire thermal boundary layer, U is equal to U infinity. Okay, so in which case eta equal to 1 you can assume, and in integrating this expression, integrating this expression, or on this page, integrating this expression for U tilde, you can entirely substitute 1. Okay, so then it becomes much simpler integration for the rest of the domain. But in the case where delta is not much less than delta t, but delta is just less than delta t, then the integration will need to be done from 0 to delta, y is equal to 0 to delta, and from delta to delta t. And here u infinity, u will be equal to u infinity, and here you will get u by u infinity is 3 by 2 eta minus half eta cube. So you have to integrate this in 2 parts and then simplify this equation in order to get the expression for the delta t, or capital delta, and the Nusselt number. So that is the expression. This is for Prandtl number less than 1 or much less than 1. So much less than 1 is simple case. You can actually neglect this integral and do only this. Or if it is just marginally less, then you need to use this and this as 2 parts of the integral. Then the problem becomes a little bit more complex, and then you need to get this. Okay. So that is the integral approach. So you see that the simplification of the profile assumption has reduced the mathematics to some extent, but not to a great extent. But with that, they are able to get the results which are not too far away from the solutions that we got from the similarity analysis. Okay. So with that, we'll take a pause in convective heat transfer. So in the next class, I will try to demonstrate the use of CFD software to solve. So far we were looking at classical methods for the laminar boundary layer. In the next class, we'll try to demonstrate the use of ANSYS Fluent or COMSOL, whichever we are more comfortable with. We'll demonstrate the solution of that for different cases, or for maybe one case we'll try to show the solution, and for the rest of it we'll allow you to explore that by yourself. Okay. So at this point we'll stop here and continue in the next class.